In this video, we will discuss section 7.2, transformation of initial value problems. So in the previous video regarding section 7.1, we introduced Laplace transforms. We discussed how to find the Laplace transform of a given function, as well as to find the inverse Laplace transform of a function. However, in section 7.1, we really didn't see how this related to differential equations in general. So section 7.2 is going to wrap it all up and show you how you can very cleverly use Laplace transforms in order to solve initial value problems. So to get started, we have a couple of pieces of information here. First, a definition says the function f is called piecewise smooth on the bounded interval from a to b if it is piecewise continuous on the interval ab and differentiable except at finitely many points, with the derivative also being piecewise continuous. So that notion of being smooth is regarding the original function f as well as its derivative. So theorem one says, suppose that the function f of t is continuous and piecewise smooth for negative t values, and so that it's of exponential order as t approaches infinity. So that there exists non-negative constants m and c as well as t, so that the absolute value of f of t is bounded above by me to the ct. So we saw this idea of being of exponential order in section 7.1. All right, then the Laplace transform of the first derivative is equal to, and let's just highlight this important formula, is equal to s times the Laplace transform of f of t minus the initial condition on f, so f of 0. And then just recall here that the Laplace transform of f of t notationally is equal to capital F of S. And so you notice that in that green highlighted equation. We have a corollary here that says, suppose that the functions f prime up to the n minus first derivative are continuous and piecewise smooth for t greater than or equal to 0, and that each of these functions satisfies the conditions in theorem 1. In other words, they're of exponential order, et cetera, et cetera. Then what this corollary does is it tells you how to find the Laplace transform of the nth derivative. So it's generalizing theorem 1. And so what you'll notice here is you have to pay close attention to the order of the derivative. And you see that occurring here as the power on s. You have your Laplace transform of the function that you're looking at, and then you continue to drop down in order of your s while also increasing on your order of your initial condition here. And so the next equality just replaces that script L notation with the capital F notation. All right, so we already understand how to find Laplace transforms of common functions. And again, that table will always be provided on quizzes, exams, or the final exam. And now we know how to compute Laplace transforms of derivatives of functions. So pulling it all together, I have this flow chart here that's going to illustrate the procedure that we're going to use to solve initial value problems using Laplace transforms. So we're going to start with an initial differential equation in X, and then we're going to apply the Laplace transform. So make sure you're applying this on both sides of the equation. If one side is equal to 0, well, we know that the Laplace transform of 0 is also 0. But if it's anything else, make sure you transform both sides. This is going to result in an algebraic equation in X of S. Now we want to solve for X of S algebraically. All right, and no calculus involved, truly just using algebra to solve for X of S. So maybe I'll emphasize here, X of S equals what? And so now we have this solution of our X of S function, and we just want to take the inverse transform to solve for X of t. So we take the inverse transform, and then we get our answer. What's really important to note here is that we took into consideration the initial conditions by the theorem 1 and corollary that utilized f of 0, f prime of 0, et cetera, et cetera. So this is the specific, or I should maybe say particular solution. And this is different from when we solve IVPs by hand without Laplace transforms. Normally, in that process, we solve for the general solution, and then we impose the initial conditions to solve for the constants of integration. That is not the case here. So what I have here is the table for common Laplace transforms. Again, this table will be provided for you whenever you need it. So it's not something that I wish you memorize, but I wanted to include it in the notes so that we can refer back and forth to it. And now I would like to take a look at a couple of problems illustrating this procedure for Laplace transforms. So let's begin here with problem number 2. I have an initial value problem. And I'd like to begin by taking the Laplace transform of both sides. So before I do that, I'm just going to individually identify the Laplace transform of x double prime using the corollary up above on page 1. So this is going to be s squared, here again where the degree on the s matches the degree of the derivative. And then I want my x of 0 here, which happens to be 3. Next, I want, excuse me, that's not what I want. I want my x of s here. So that's just the Laplace transform of little x of t. Then I want to subtract off, drop one exponent on the s, and then I want to multiply by my x of 0, which is 3. Finally, we're down to s to the 0th power, which is just 1, and then subtract off my x prime of 0. All right, and so I can rewrite this as an s squared x of s minus 3s minus 4. I don't need the first derivative, and of course, I know the Laplace transform of x is just capital X of s. So I'm ready to move forward here. Applying the Laplace transform on x double prime plus 9x equals 0, we get s squared x of s minus 3s minus 4. Then I need to add 9x, but when I transform it, it's 9 capital X of s. And then, of course, the Laplace transform of 0 is 0. So what I'm going to do now is I'm going to take the terms that do not include an x of s. I will move those over to the right-hand side, and I'm going to factor out my x of s on the left. And so solving algebraically for x of s, I obtain that x of s is 3s plus 4 divided by s squared plus 9. So from here, my goal is to find the inverse transform of this function. So in order to do that, I'm going to manipulate this a little bit. I'm going to divide this into two fractions, 3 times s over s squared plus 9, plus 4 times 1 over s squared plus 9. And when I look back up here at the table of Laplace transforms, I'm going to color code here. I see this in green corresponds to the cosine function. And in yellow, it doesn't quite match any of these, but it's closest to the sine function. So all I'm missing on top is a k value. In this case, k squared is 9, so k is 3. So I'm going to force a 3 on the numerator, but I'm going to pay for it by dividing by 3 as well. So I'm just rewriting my first term, and then I'm going to write this as a 4/3 times 3 over s squared plus 9. And now I can apply the inverse transform. And I conclude that x of t is 3 times, here again, looking up top, that was a cosine of 3t. And carrying my 4/3, 3 over s squared plus 9 is a sine of 3t. So you can see at this point, there are no constants that I need to solve for. That was all taken care of when I transform the derivative. It utilizes those initial conditions right there. So this process avoids any heavy calculus machinery. There's no integration or anything of that nature. We're just doing some algebra as well as utilizing our knowledge of Laplace transforms. All right, so next number 4 is very similar to the previous problem. I'm going to start by finding the Laplace transforms of the two derivatives. So let's find the Laplace transform of x double prime. Here again, that's s squared times x of s minus s times the initial condition on x, which is 2, minus the initial condition on x prime, which is -3. So what I'm getting here is s squared x of s minus 2s plus 3. And now let's also find the Laplace transform of the first derivative. That is s x of s minus 1 times 2. So I get s x of s minus 2. All right, so pulling it all together, I'd like to find the Laplace transform of this entire dE. X double prime plus 8x prime plus 15x equals 0. And so that is going to give me s squared x of s minus 2s plus 3. Now I need to add 8 times the Laplace transform of the first derivative. So plus 8s x of s minus 16. And then plus 15 x of s. And here again, the Laplace transform of 0 is 0. I am going to move the highlighted terms to the right-hand side and factor the x of s out on the left. So that's going to leave me with s squared plus 8s plus 15 equals 2s plus 13. All right, so I'm going to go ahead and divide here to solve algebraically for x of s. And I'm just going to go ahead and factor that denominator. That factors to x plus 5, s plus 3. And in order to find the inverse transform, I'm going to have to split this up by way of partial fractions. So since these are linear factors, I'll write it as a over s plus 5 plus b over s plus 3. And so solving here, I have 2s plus 13 equals a times s plus 3 plus b times s plus 5. And so I'm going to plug in the roots of the factors. If s equals -3, then my left-hand side is -6 plus 13, so 7 equals 0 plus 2b. So b equals 7 halves. If s equals -5, then I have -10 plus 13, or 3, equals -2a plus 0. So a equals -3 halves. So if I plug that back into my x of s equation, I'm going to write this as -3 halves times 1 over 1 plus s, or excuse me, 1 over s plus 5, plus 7 halves 1 over s plus 3. And so now I would like to take the inverse transform of this, and that's going to leave me with my final answer. So I'm going to recopy my coefficient. And the question is, what is the inverse transform of 1 over s plus 5? So I'm going to scroll back up to the table of transforms. And I'm going to write off to the side what we have is 1 over s plus 5. That appears to be closest to this formula. So I could rewrite it as 1 over s minus a -5. And so we see that -5 is going to go up inside the exponential, e to the -5t. And in the same vein, we get 7/2 e to the negative 3t. So here again, this is our particular solution for this initial value problem. It is pretty slick working with Laplace transforms. All right, I'd like to do one more example in this video, and that will conclude part 1 of this section, and then I'll handle the last 2 pages in a subsequent video. So let's take a look at problem 6. One noticeable difference here in this problem is that we have a cosine t function. And so we're going to have to incorporate that when we take the Laplace transform of both sides. So to begin, let's find the transform of x double prime. So that is going to be s squared x of s. And notice that all of the initial conditions are 0, so both of those last terms zero out. And now let's take the transform of the entire equation. So that's going to give me my s squared x of s plus 4x of s equals, I need to know what the Laplace transform of cosine t is. So let's scroll back up. Cosine of t is going to be s over s squared plus 1. So I'm going to add that in, s over s squared plus 1. Okay, so here again, we just want to divide through once we've factored out an x of s. So that leaves me with a factor of s squared plus 4. So I conclude that x of s is s over s squared plus 1 times s squared plus 4. All right, so now I would like to compute the inverse transform. This one's going to be a little bit trickier because to separate it, I'm going to have to use partial fractions. But in this case, what we have is irreducible quadratic factors. So let's actually scoot this all over a little bit to give us a little bit more room to write out the partial fractions. And so I'm going to set up my partial fractions. Because these are quadratic, the numerator is an as plus b over one of the terms and a cs plus d. Okay, so remember when you have quadratic factors, no longer do you just have an a and b on top, you have a linear combination. All right, so we would like to solve for a, b, c, and d. So I have s equals as plus b times s squared plus 4 plus cs plus d times s squared plus 1. All right, and so you can go about solving for these coefficients in a couple different ways. Um, Oftentimes, students will expand this out and equate coefficients, which is perfectly fine. Because we're working with complex numbers in this semester, I feel okay with evaluating at the complex roots. So I'm going to choose to evaluate at s equals I and s equals 2I. So let's go ahead and do that. If s equals I, what do we get? So on the left-hand side, we have I. On the right-hand side, I have AI plus B times I squared is -1, so I get 3, and the other term drops out. So I have I equals 3AI plus 3B. So I can now solve for A and B. 1 has to equal 3a if I equate the coefficients in front of I. So a equals 1/3, and since there are no constants on the left-hand side, b must equal 0. So I solve for 2 there just by using that one root. Let's do the same for 2i. So if I plug in 2i for s, I get 2i equals, the first term drops out. The second term is a 2ci plus d times 2i squared is a negative 4 plus 3 or plus 1 is a negative 3. So I have 2i equals negative 6ci minus 3d. So here again, by equating coefficients, I get that c equals negative 1/3 and d equals 0. So where we are is x of s equals, I have 1/3 times 1 over s squared plus 1, as well as a negative 1/3 1 over s squared plus 4. So I just need to work here with this. Oh, and I just noticed I dropped my s's, so let me add those in here. Should be an s on top of both of them. A and C were coefficients of the s term. All right, so at this point, we can look and see which function this corresponds to for the inverse. S over s squared plus k squared. We're looking at this green equation with cosine, and we just need that k value stuck inside. So if we come back down here, applying the inverse transform, we get x of t equals 1/3 cosine t minus 1/3 cosine 2t. And this is our solution to the IVP. This concludes our video for part 1 of transformations of initial value problems, and we will finish the second two, or the last 2 pages of the notes in the part 2 video.